you know, just simply trying to calculate rate times time equals distance. We have to add something in called acceleration, okay? Which we're going to signify as an A. And the units, since we're talking about units, is going to be a distance, okay, divided by a time squared. In physics, we normally signify that by using So I'm just reading the chats here. I haven't been looking at the chats, but we got a sweet, and then we got you two are so handsome, dude.
I just read that too.
And then we got a didn't realize my second question had such even numbers.
Well, if you want not even numbers, type it in the chat.
Yeah. Give us something real hard. And then, so anyways, we got a distance divided by a time squared. Normally in physics, this is going to be in meters divided by seconds squared. And what the acceleration is it's how quickly your velocity is changing, right?
Right.
So if you've got a car that's traveling this direction, right, it's going to have a velocity associated with that v. But if it's slowing down, you're going to have this minus a term, right? And so it's going to get slower and slower. Well, if we draw these three things out on a graph together, I'm going to draw a pre-graph here. Ooh, let's get some graph paper. Thank you.
There you go.
So in this situation that I'm talking about where you have a negative acceleration, something's slowing down, so we're going to start with the blue color is going to be distant, or we're going to start with acceleration, okay? So we're going to say we have a negative 1 meter per second squared acceleration, okay?
Okay.
So it's just going to be this flat line, okay? Like this. And our x-axis, by the way, is time, okay?
Our x-axis is time.
And our y-axis is going to be different depending on each thing we're going to look at here, okay? So that's...
So we'll talk about acceleration, velocity, and displacement.
Yeah, exactly.
Okay.
And so if we look at this, let's say our velocity started with, what is that? That's 1, 2, 3. Okay, we got a velocity of 3 to start out with. That's going to be in meters per second. But it's slowing down, right, with an acceleration of 1 meter per second squared. And so what that actually means is that if you look at this, that means that every second that this thing travels, it's going to slow down by 1 meter. So we'll go over, or 1 meter per second. So we go over 1 and down 1, over 1 and down 1, like this, and we get this line that looks like this. This is our velocity graph, okay?
Right.
And then, let's throw in some yellow here for our distance.
Look at these fancy colors here.
Yeah, and so our distance is going to look something, our displacement is actually going to look like something like this. If we start at 0, it's going to start going up, right? And our displacement's going to start going up, but it's going to start flattening out, and that's not entirely correct here. It's going to flatten out when our velocity hits 0, so right there, and then afterwards our displacement's going to start going back down, because as we've talked about a lot in this course, there's no way to really signify which way something's moving with numbers other than its sign. So when we get to a negative velocity, that actually means that the object is going to start moving backwards in time. Or not in time, sorry, we'll move backwards with its direction. And so you get this kind of...
You solved time travel, dude.
Dude, yeah, I did. I'm super smart, man. Okay, so
Yeah.
if we want to take this even further, Jaden, you know calculus, so we're going to talk calculus for a second here. All right.
Hey, I like calculus. Yeah.
Okay. So if you look at this, Jaden, and just looking at what you know about calculus, if you look at your acceleration and look at your velocity, do you see any correlations between the two if it was in calculus?
Well, yes, I do. So if you take derivatives and integrals, right, that's so the velocity, if you take the derivative of that, you get acceler. Wait, or is it the other way around?
So if you take the integral of acceleration, right, you get
You get velocity.
velocity, okay?
Yes,
And if you take the integral of velocity, you actually
you
get
get
the displacement.
displacement. Yes,
So if we take the integral of a, this equals v, and if we take the integral of v, this equals d. Do you like my notation there? Super accurate. Sorry, this is
yeah.
there's a really important factor here. Very important thing that I forgot. This is with respect to time. So it's dt equals v of
Yeah.
t, and this is v
And
dot
then you can
dt.
add plus C. What does that plus C mean?
So that plus c is a constant, okay? And I actually had this question the other day, um, and trying to figure out what that plus c is. And what that
Okay.
plus c is so as you see, we've got this v of t equals plus c. And so if we were to say t equals 0, um, actually, well, I mean, so if we were to actually write this out, it would become, the integral of a would become at plus c, right? And this is equal to v of t, like that. That's technically the right way to write this out, okay? Right, if you actually took the integral, you'd get a of t plus c equals v of t. And so if we
Okay.
were to say t equals 0, this term right here, a of at would go to 0, right? So you'd get 0 plus c equals v of t, or v of 0, sorry. So what c actually
Right.
equals is your initial velocity. So
Okay.
what speed you started out with. Um,
Nice.
and then if you take it again, if we take this integral again, so if we take the integral of a of t plus c, and we're going to change this because we just proved that this is vi, so we're going to say that this is vi, and this is dot dt. If we take the integral of that, we get 1/2 a t squared plus vi t. I'm going to rewrite this down here a little bit because I'm running out of room again. We
Yeah.
get 1/2 a t squared plus vi plus c, or I guess we'll use a different constant now. We'll call this d.
Put in the T with the VI term.
Thank you. Equals,
Yeah.
we'll call it capital D for displacement. And if you look again, this constant little d, if you notice, when we plug in a 0 here, these are all going to be 0 again. And so this d term is actually going to be our initial starting point.
Ah,
So, and
that's
if
very
you,
fancy.
it is pretty fancy. And the other thing to notice is, remember the original equation that we had to solve the last problem was Vt equals D, right? I guess we change this to big D. Or we'll just call it D of T. Um, and if you notice, that is actually this term right there. So this is the term without acceleration associated with it, but we actually have to
Okay.
account for it for acceleration, and so this is where that term comes into play.
Okay. So in real life, we are always changing speed and direction, and that is what causes this acceleration term to actually matter in everyday life, right?
Right, because like when you, let's say you're at a stoplight, right? You're gonna have to speed up, right? And
Right.
then, and so there's an acceleration. It's something we all are very familiar with. You know, when you're driving, you feel it, you know it's there. Um,
Okay.
but you know, for the most part, that question that we solved is very simple. But when you're on a freeway and just going along, I call it, you know, it's like the human conveyor belt, right? You just hop on and just go. You could get pretty
Right.
close to um, not having any acceleration to worry about.
Yeah, that's what we did at the beginning is a really good approximation if you're on a freeway, right? If you're
Right.
just traveling pretty close to the same speed, that time that we gave you is going to be pretty accurate.
Exactly.
Okay.
Cool, cool. Where do we want to go from here?
Are there any other questions? Not yet.
Not yet.
Okay.
Here, dude,
Okay. Well,
I'm gonna push mathematical again.
it, I would say what you just explained and taught us was more mathemagical, dude.
You think, dude?
Yeah.
Dude, there's no such thing as magic.
Oh, right. I like how like some professors, if they're like, "Oh, I don't actually want to prove this," or just like do some hand waving, and then
Yeah.
they're like, "Here's the answer," and you're like, "Wait a second."
Dude, that drives me insane when people do that. They're like, yeah,